There is nothing in the codebook stating that the total amperage of all the circuit breakers combined can equal a certain amount. However, Article 408 of the National Electrical Code does require that the size of the service conductors be based on the total calculated load of the installation. According to Table 408.3, B, the combined load for a dwelling unit is calculated by multiplying the square footage of the dwelling by 3 volt-amperes per square foot. For example, a 2,000 square foot dwelling unit would have a calculated load of 6,000 volt-amperes. Once the total calculated load has been determined, the size of the service conductors can be selected from Table 310.15. B16. For a load of 6,000 volt-amperes, the minimum size service conductors would be 100 amps. Therefore, if there is a 200 amp main panel, it is necessary to ensure that the total calculated load of the installation is not greater than 6,000 volt-amperes. If the total calculated load is greater than 6,000 volt-amperes, it would be necessary to upgrade the size of the service conductors in the main panel. To elaborate, the National Electrical Code, or NEC, establishes the standards for safe electrical installations. It's not about the sum of the breaker ratings, but about calculating the actual load the service will experience. The NEC provides methods to estimate this load. Article 408 addresses switchboards, switchgear, and panel boards. Table 408.3. B provides a means of calculating the general lighting load for dwelling units, which is where the 3 volt-amperes per square foot comes from. This is a simplified calculation for general lighting and receptacle outlets. It does not cover major appliances, heating, air conditioning, or other large loads. For these, specific calculations are required as per other articles in the NEC. Now let's delve deeper into load calculations. The NEC mandates a calculated load that accurately reflects the anticipated electrical demand. This ensures that the service conductors and equipment are adequately sized to handle the load without overheating or causing voltage drop. The process typically involves several steps. Firstly, determining the general lighting load, as previously discussed, using the square footage method. Secondly, calculating the appliance load, including both small appliance circuits and individual appliance loads. Small appliance circuits in a dwelling unit, which serve kitchen and dining areas, are calculated at 1500 volt-amperes per circuit. Individual appliances, such as ranges, dryers, water heaters, and air conditioners, are calculated based on their nameplate ratings. Specific demand factors are permitted for certain appliances, like ranges and dryers, recognizing that they are not all used simultaneously at their maximum rating. Thirdly, calculating the heating and air conditioning load. The larger of the heating or cooling load is added to the other loads. The NEC provides specific rules for calculating these loads, taking into account the type of heating and cooling system and the climate. Fourthly, considering other loads, which may include electric vehicle chargers, swimming pool equipment, or other significant electrical loads. Each of these loads is calculated based on its specific characteristics and usage patterns. After calculating all the individual loads, demand factors are applied to certain loads, as permitted by the NEC. Demand factors recognize that not all loads will be operating at their maximum simultaneously. This allows for a more realistic estimate of the total load. Once the total calculated load is determined, the minimum size of the service conductors is selected from Table 310.15. B16. This table provides the allowable ampacities of insulated conductor based on their size, insulation type, and installation conditions. It's crucial to select conductors with an ampacity equal to or greater than the calculated load. In the example of the 2,000 square foot dwelling unit with a calculated load of 6,000 volt-amperes, the minimum service conductor size would be 100 amps, as per Table 310.15. B16. Assuming copper conductors with a temperature rating of 75 degrees Celsius are used. However, it's important to note that this is just the minimum size. Depending on the specific installation conditions, voltage drop considerations, and future load growth, it may be necessary to use larger conductors. Now let's address the 42 overcurrent device limitation mentioned earlier. Section 408.35 limits the number of overcurrent devices in a panel board to 42. This limitation is intended to prevent overcrowding of the panel board, which can make it difficult to access and maintain the breakers. This limit does not, however, relate directly to the total amperage of all breakers combined, but rather the physical number of breaker spaces in the panel. A single breaker can occupy 1, 2, or 3 spaces depending on if it's a single, double or triple pole breaker. The rating of the individual breakers is determined by the loads they serve and the wire size of the branch circuits, not by a ratio to the main breaker. It is important to understand the difference between the calculated load and the sum of the breaker ratings. The calculated load is an estimate of the actual electrical demand based on the anticipated usage patterns of the dwelling. The sum of the breaker ratings, on the other hand, is the total capacity of all the branch circuits in the panel board. The sum of the breaker ratings will typically be much higher than the calculated load. This is because each branch circuit is protected by a breaker that is sized to handle the maximum current that the circuit is expected to carry. However, not all of the circuits will be operating at their maximum current simultaneously. For example, a kitchen circuit might have a 20 amp breaker, but the actual load on the circuit might only be 5 amps at any given time. If the total calculated load is greater than the rating of the main breaker will trip, interrupting power to the entire dwelling. This is why it's crucial to accurately calculate the load and select a main breaker that is appropriately sized. In the scenario where a 200 amp main panel is hypothetically loaded with a total combined amperage of 300 amps with all the breakers combined, it doesn't automatically mean that the installation is unsafe or non-compliant. The crucial factor is whether the calculated load exceeds the ampacity of the service conductors or the rating of the main breaker. If the calculated load is within the limits, the installation is likely safe, even if the sum of the breaker ratings exceeds the main breaker rating. However, it is vital to verify that all branch circuits are properly sized and protected, and that the overall installation complies with all applicable NEC requirements. Here's a more detailed look at how to apply demand factors. Demand factors are multipliers that reduce the calculated load based on the assumption that not all loads will operate simultaneously at their maximum. The NEC provides specific demand factors for various types of loads, such as ranges, dryers, and heating and cooling equipment. For example, Table 220.55 provides demand factors for household ranges. The demand factor varies depending on the number of ranges and their individual ratings. For a single range rated at not over 12 kilowatts, the demand factor is 8 kilowatts. This means that instead of calculating the range load at its full nameplate rating, you can use 8 kilowatts in the load calculation. Similarly, Section 220.54 provides a demand factor for clothes dryers in dwelling units. The demand factor is 5 kilowatts, which means that you can use 5 kilowatts in the load calculation instead of the dryer's full nameplate rating. It's essential to apply the correct demand factors to ensure an accurate load calculation. Using overly conservative demand factors can result in an oversized service, which is unnecessary and costly. Conversely, using demand factors that are too low can result in an undersized service, which can lead to overloading and potential safety hazards. In addition to demand factors, the NEC also allows for diversity factors to be applied in certain situations. Diversity factors are similar to demand factors, but they are typically used in commercial and industrial applications where there are multiple loads of the same type. For example, a commercial building might have multiple HVAC units. The NEC allows for a diversity factor to be applied to the total HVAC load, recognizing that not all of the units will be operating at their maximum simultaneously. The specific diversity factors that can be used will depend on the type of load and the specific requirements of the NEC. It's crucial to consult the NEC and any applicable local codes to determine the appropriate demand and diversity factors to use for a particular installation. The proper application of demand and diversity factors is essential for ensuring an accurate and safe load calculation. Let's also discuss the importance of voltage drop. Voltage drop is the reduction in voltage that occurs as electricity flows through a conductor. Excessive voltage drop can cause lights to dim, motors to run inefficiently, and appliances to malfunction. The NEC recommends limiting voltage drop to 3% in branch circuits and 5% in feeders. To minimize voltage drop, it's essential to select conductors that are large enough to carry the load without excessive voltage drop. The longer the conductor, the greater the voltage drop. Therefore, it's crucial to consider the length of the conductor when selecting its size. The NEC provides formulas and tables for calculating voltage drop. These tools can be used to determine the appropriate conductor size for a particular load and distance. In addition to conductor size, other factors can affect voltage drop, such as conductor material, temperature, and frequency. It's essential to consider all of these factors when designing an electrical system to ensure that voltage drop is within acceptable limits. Now let's consider future load growth. When designing an electrical system, it's crucial to consider the potential for future load growth. Dwelling units often undergo renovations or additions that increase the electrical load. It's essential to select service conductors and equipment that are large enough to accommodate future load growth without requiring costly upgrades. A good rule of thumb is to add 25% to the calculated load to account for future growth. This will provide a buffer that can accommodate most reasonable load increases. In addition to future load growth, it's also important to consider the potential for changes in technology. New appliances and equipment are constantly being developed, and these new devices may have different electrical requirements than older devices. It's essential to stay up to date on the latest technology and to design electrical systems that can accommodate these changes. For example, electric vehicle chargers are becoming increasingly common in dwelling units. These chargers can draw a significant amount of power, and it's essential to factor this load into the service calculation. Designing an electrical system that can accommodate future load growth and changes in technology will ensure that the system remains safe and reliable for many years to come. Furthermore, it's crucial to understand the role of the electrical inspector. The electrical inspector is responsible for ensuring that electrical installations comply with the NEC and any applicable local codes. The inspector will review the plans for the installation and conduct on-site inspections to verify that the work is done properly. It's essential to work closely with the electrical inspector throughout the design and installation process. The inspector can provide valuable guidance and help to ensure that the installation is safe and compliant. The electrical inspector has the authority to reject any work that does not comply with the code. Therefore, it's crucial to address any concerns or issues raised by the inspector promptly. Obtaining the necessary permits is an essential part of the electrical installation process. Permits are required for most electrical work, including new installations, modifications, and repairs. The permit process typically involves submitting plans to the local building department for review. Once the plans are approved, a permit will be issued, allowing the work to proceed. Permits are important for several reasons. Firstly, they ensure that the work is done safely and in compliance with the code. Secondly, they provide a record of the electrical work that has been done. Thirdly, they protect the homeowner from liability in case of an accident or injury. Failing to obtain the necessary permits can result in fines, delays, and even legal action. Therefore, it's essential to check with the local building department to determine the permit requirements for a particular project. Let's also address some common misconceptions about electrical load calculations. One common misconception is that the service size should be based solely on the size of the main breaker. As discussed earlier, the service size should be based on the calculated load, not the main breaker size. Another misconception is that the sum of the breaker ratings should equal the service size. This is also incorrect. The sum of the breaker ratings will typically be much higher than the service size. A further misconception is that demand factors are always safe to use. While demand factors can be used to reduce the calculated load, it's essential to apply them correctly and to consider the potential for future load growth. Avoiding these misconceptions will help to ensure an accurate and safe load calculation. In summary, determining the appropriate service size for a dwelling unit involves a comprehensive load calculation that takes into account all of the electrical loads in the dwelling, including lighting, appliances, heating, and cooling. The NEC provides specific rules and guidelines for calculating these loads, and it's essential to follow these guidelines carefully. Demand factors can be used to reduce the calculated load, but it's important to apply them correctly and to consider the potential for future load growth. Voltage drop is another important factor to consider when designing an electrical system. The service conductors and equipment must be sized to minimize voltage drop and to ensure that the voltage at the point of use is within acceptable limits. Working closely with the electrical inspector and obtaining the necessary permits are also essential parts of the electrical installation process. By following these steps, it's possible to design an electrical system that is safe, reliable, and compliant with the NEC and all applicable local codes. Understanding the principles of electrical load calculations is essential for anyone involved in the design or installation of electrical systems. This knowledge will help to ensure that electrical systems are safe, efficient, and able to meet the needs of the occupants. Remember to always consult the latest edition of the National Electrical Code and any applicable local codes for the most up-to-date requirements. Electrical codes and standards are constantly evolving, so it's essential to stay informed about the latest changes.